This is Mr. Hobbs AP Chemistry class. Feel free to subscribe. Yesterday, we're starting to work on these problems. Okay, so I want to look at a few of them and make sure we started in. I put a few of. What are you laughing at? Because this looks funny hanging down there.
No, she made a joke.
But you think I do that all the time. I think it's hilarious. I crack myself up. Okay, so let's just look at these and make sure that we're getting these correctly. Okay. And if you have your Chromebook, pull the Chromebook out, because I'm not going to shine these up. Oh, I sure wish I had my glasses up here. So here's the plan. Listen, here's the plan for today and tomorrow. Okay? Today we're going to kind of look at these problems. I'm going to introduce just a couple of more ideas. They're simple. Okay? We're going to do more practice problems then during the last half to 3/4 of the class. Probably last half of the class is going to be more practice problems. Tomorrow we're going to come in. Y'all listen, gentlemen. And we are going to go in and do a lab, but it's going to be just a learn technique lab. We're going to make solutions lab, like sugar and salt solutions. Just learn and try to actually, some of these problems that we're going to be working, try to actually just do some of them, just kind of, so it means more than just words. Okay? So just try to get, but the good thing is you'll write it in your lab manual, but you're not even ever going to turn it in or anything to me on that, because we're just learning technique. Then the next lab that we're going to do, you'll have to make solutions, and we're going to measure the concentration of them. But then hopefully by that point, you'll be more comfortable making them, and you'll make them better and get better results. All right? So Friday then is going to be a tie up loose ends day. Okay? Monday will probably be, what will Monday's date be?
3rd.
Oh, crud. Okay? Now, probably just to make life better, I don't know. Do you guys, you don't have any ideas yet what your test schedule is next week?
It's probably going to be bad.
It's probably going to be bad because it's the last week of the 9 weeks. Well, vocab quiz you're going to have every Monday type thing, so. You don't have a vocab quiz every week?
We should. We have one every 2 weeks. I do.
Okay. Now.
Probably going to have an engineering test.
Yeah, you're probably going to have a test in every class, but I'm going to try and not pile on Thursday. So we're going to wait. We're going to wait and see where we are kind of at the end of the week. It might end up being Monday. Math test will either be Tuesday or Thursday. Well, let me say that. It'll be Tuesday, Wednesday, or Thursday, depending on whether you're Wednesday, Thursday on your math. Okay? So, I'm just going to try not to pile on, but that just means, listen, that just means that there's a possibility of a test Monday. Now, I told the other class this as well. We are going to be needing the Princeton Review very soon. Okay? So if you haven't ordered or gotten the Princeton Review yet, the 2017 edition, it's cracking the AP Chemistry. You need to start thinking about getting that, so you have time. So if you don't have Amazon Prime, you don't have to pay for overnight shipping and all that kind of stuff. If you're one of the first 2 or 3 to Books A Million or Barnes and Noble, then you can get the 2 that are on their shelf. But it's cheaper on Amazon. Just start that process. Next unit, we're going to start using it. All right. So I just want to give you the heads up there. I told you at the beginning of the year you were going to need it, but we weren't needed immediately. I'm telling you now, giving you heads up, because once we do start doing an assignment out of it, if you don't have it, you just get the 0. All right? So don't wait until the last minute. We want the Princeton Review, AP Chemistry Review Book, 2017 edition. 2017 edition. Okay? So, I believe that I had 21, 23, 26 on the board for you yesterday. Okay? So, if you want information about those, you can just check with me as we're working on the other ones. But now let's look at 27. That says, separate samples of a solution of an unknown salt are treated with solutions of HBr, H2SO4, and NaOH. Okay? So of an unknown salt. So one thing is treated with these three things. A precipitate forms in all three cases. Which of the following cations could be present in the unknown solution? So we could have 27. We could have potassium. We could have lead. Or we could have, it's barium, I believe. My short-term memory serves me right. Barium. Okay? And we're going to treat it with HCl, H2SO4, and NaOH. And only one of these forms a precipitate with all three. Yes, ma'am. HBr? Okay. It wouldn't matter, but it's good to know. Okay, so Anthony, let's get some focus now. Okay? Well, you're just ping-ponging back and forth between both sides. I said he was. Okay? So, when we look at this, we want to know which one of these will form a precipitate with all three things. Now, first off, these are all positive, so which anion are they going to want to combine with? The negative one, right? I heard somebody say that. So, that means that K plus is going to go with Br minus, K plus is going to go with SO4 2 minus, and K plus would go with the OH minus. Now, would any of those be a precipitate? Why? K is an alkali metal. All alkali metals are always soluble. So anything, potassium, anything is soluble, means it won't form a precipitate. So no precipitates with this one. Okay? But what about the lead? The lead goes with the bromide. Would that be a precipitate? Yes. So what would the precipitate be? PbBr2. Okay? What about Pb with SO4? Would that be a precipitate? PbSO4. That's one of our common sulfate precipitates. And what about PbOH? PbOH2. Solid. So that would make a precipitate with all three. So you don't even really have to write the equations. If you just kind of start understanding how the ions are going to combine, you can start doing some of this just in your head. Okay? Now what about barium? Barium bromide. Is that one of our three, or really two common halide precipitates? No, it's silver, lead, and mercury. But again, nobody deals with mercury. So silver and lead chloride, bromide, and iodide are the common precipitates. Okay? Would barium sulfate be a precipitate? Yeah, we'd get a precipitate of barium sulfate. Okay? What about barium hydroxide? That's one of our 7 strong bases, right? So that means it's soluble. That's one of the 7 hydroxides that actually are soluble. So we only get one precipitate with the barium. Barium hydroxide. Okay? Not barium hydroxide, Steve. Barium sulfate. Sorry. I generally don't call myself Mr. Hobbs.
I think your name's Steven.
Steven, it's the same thing. Steve is short for Steven. When I write my name, it's Steven. When I talk and introduce myself, it's Steve. Depends whether she's mad or not. Usually she calls me by my brother's name. because she couldn't. Yeah, I was the last of 5 kids. I got called just about any of them. Okay, does everybody? Hey, listen. Shh. Come back to me. Does everybody understand the thought process? Y'all, it's the thought process that's most important. Positive ion is going to go with the negative one. It's all about the solubility rules. Okay? So now you look at 39. 39 says, now complete and balance the following molecular equations, then write the net ionic. Okay? So we have HBr plus calcium hydroxide. Now, several of you asked me, is calcium hydroxide soluble? Okay? And the answer is kind of. If you notice on here, it says forms slightly soluble compounds, solubility less than 0.1 molar. Huh? Why can't I just talk and you guys not say something? 0.1 molar. Okay, forms slightly soluble compounds, solubility less than 0.1 molar. That doesn't mean they're completely insoluble. There's gray areas. Calcium hydroxide fits into the gray area. Y'all, turn around and listen to me. Okay? If all y'all are making 100% on the test, then we could just have all this little whatever. Okay? Let's get some focus. I promise you, you're going to have your free time. Okay? Just focus for a second. The 0.1 molar. That's just kind of a cutoff to where we say it's soluble or insoluble. Calcium hydroxide is right on that borderline. Some books say it's soluble, some say it's insoluble. It's kind of soluble. Some will dissolve, but not a whole lot. So some place it somewhere in the middle between whether it's a strong base or it's not a strong base. The AP test gives you credit for both if you break it apart or you keep it together. It doesn't matter. They usually don't use it because it's kind of in that gray zone. So, but this book put it as aqueous because it makes the problem easier. So what does that give us? Calcium bromide. And what's the formula of calcium bromide going to be? How do we know it's Br2? Okay, so Morgan, how?
The charge of calcium is plus 2.
How do you know the charge of calcium is plus 2 without memorizing it? It's in the second column. How do I know bromide's minus 1 without memorizing it? It's a halogen. Okay, so we need to all know that. So we balance charge first, so it's CaBr2 plus H plus, OH minus makes water. And so I'm actually going to write it HOH. Now, is calcium bromide one of our common halide precipitates? What are the 2 common halide precipitates? Silver and lead. Silver and lead. Calcium's not one of them, so calcium bromide's aqueous. Now I need to balance it by 2 there and 2 there. So how do we shortcut? How do we know which one is going to be my spectator ions? Which ones are going to be the spectator ions?
The ones that are present and the ones where the state is changed.
Okay? I think those are the ones where the state is changed is the ones that not going to be the spectators. Okay? The other ones will be. So the thing that's still aqueous, the thing that's still dissolved, where the ions are still just floating around. So the calcium and the bromide are going to be just floating around. Now, what type of substance is HBr? What's the name of it?
Acid, bromide.
It is an acid. It's hydrobromic acid. Okay? So, is that a strong acid? Yeah, it's one of our 6 strong. So, that breaks apart. 2H plus 2Br minus, plus, this is going to break apart, Ca2 plus 2 OH minuses, goes to Ca2 plus 2 Br minuses, plus 2 HOHs. And everything else is aqueous. So what's the spectators? We already kind of said. Calcium and bromide. So we're left with 2H plus, 2OH minus, going to 2HOH. Okay, ladies? Yes?
Why do you keep it? Why can't you change HOH to H2O?
You can. 100%.
Why
do I? Because I want you to see that the H plus is coming from the acid combining with the OH minus from the base. And so it's a double replacement. When you see H2O, you think it's hydrogen and oxygen. But the reality is it's an H plus ion and a hydroxide ion coming together. All right? So it's just a way to kind of keep track of your ions when you're doing the double replacement. It doesn't matter either way, 100%. Okay? So, notice again, we'll cancel out the 2's, and we want to reduce it to the lowest possibility. Now, all of those are going to be like that, except when you look at copper 2 hydroxide, it's a solid, so would it be together or apart? Together. But you're still going to make the copper perchlorate and then water. And then aluminum, that's aluminum hydroxide, that's a solid as well. So that's going to be together. So you're just going to have the base is going to be together rather than apart on this one. So what's the only spectator ion in those two? The anion that's with the strong acid. Okay? That's going to be the only spectator. All right. So the rest of those are really more just writing and balancing the equations, and we can come back and check those. So for today, we need to talk about how to dilute a solution, okay? And tomorrow we're going to practice doing that. And a dilution, we're still under concentration. I'm talking about molarity. What does it mean to dilute something? Make it less concentrated by adding water. You add water to it, it becomes less concentrated. Okay? Now the water is going to be homogeneous. So it's a real simple thing. Molarity times volume always equals moles. Okay? When you just add water, the moles don't change, but the liters change. You go from a small volume to a larger volume, but the moles stay the same. And so it's a simple formula where we can say the molarity of the concentrated times the volume of the concentrated is equal to the molarity to the dilute times the volume of the dilute. Molarity of C equals concentrated. D equals dilute. Okay? C equals concentrated, D equals dilute. So, if we just want to figure out how much we have to add and whatever, and I'd have to do this all the time again when I'm diluting acids, because if we want all the acids I buy are in concentrated form, because it's cheaper to buy 18 molar H2SO4. The HCl is 12 molar, the HNO3 is 14.3 molar. So you have to just kind of go through and do the dilution. Okay? So, the question would be, how many milliliters of 18 molar H2SO4 are needed to make 500 milliliters of 3 molar solution of 3 molar H2SO4? So, what's my concentrated here? What's the molarity of the concentrated? 18. What's the volume of the concentrated? That's what you're looking for. Okay? What's the molarity of the dilute? 3. What's the volume of the dilute? 500. Now the good thing is, since it's a ratio, we don't even have to change it from milliliters. We don't have to go to liters. So we say the molarity of the concentrated, 18 molar, times the volume of the concentrated is equal to the molarity of the dilute times the volume of the dilute. So really, we're just going to be going to 3 divided by 18. So the volume of the concentrated is 3 times 500 divided by 18 molar. So that's going to equal, it's going to be 1/6, 500 divided by 6, which is going to be, 6 goes into 58.833. No, it should be 83.
83.
83 or 8.3?
83.3.
Okay, so what does that mean?
If you want a 500 milliliter for you,
Okay, wait, one at a time. So what do we do? 83.3 milliliters of
18 molar.
18 molar. So I go to this on my acid cabinet. I grab the bottle of concentrated H2SO4. It's 18 molar in the bottle. I measure out 83.3 milliliters into a 100 milliliter graduated cylinder. Okay? So I go to 83.3 milliliters. Okay? So now I need 500 milliliters, right? Do I add 500 milliliters of water?
No, so you added to like a 500 milliliter beaker.
Okay, well, we wouldn't want to use a beaker, so what I'm going to do is I'm going to use a 1,000 milliliter graduated cylinder. And I'm going to have 500 is going to be right here. Now, do we add acid to water, water to acid? Does it matter? Do what you oughta. Add the acid to the water. Okay? Now, it's because it gets extremely hot. So we need to have the water to dissipate the heat. So what we would do is we'd fill this up to about 300 milliliters with just distilled water. Then you pour this into it, and it's going to bring it up here. Let the heat, and you pour it down the side, let it add in slowly. Then you just slowly bring it back, and then you use, if you pour a jug or you can just use a squirt bottle, you fill it up to the 500. So you don't add 500 milliliters of water, you add the water until it gets to 500. Because there is a tricky multiple choice question on AP that says how much water has to be added, okay, to make 100 milliliters of the solution. Well, you do the molarity of the concentrated, you do this equation, and you find out the answer comes out to you need a total volume of 100, but you started with 10, so you only have to add 90. So the question is asking for adding 90, not what the total volume is. Anyway, I'll give you an example of that.
So how much? So you know how you said you add water after you pour in?
Yeah.
You pour more water to get to 500.
To 500.
But why don't you just measure out that 400 low?
Because it's just a lot easier just to put some in.
But I thought you can't pour water into acid.
Well, do what you ought to add the acid to the water, but once you have the heat dissipated, adding more water to it then isn't going to be a problem. So you're adding the acid to the water to dissipate the heat. So the heat of the solution, so when sulfuric acid dissolves, it gets extremely hot. What does that mean then in terms of the solution process? Solute, solute, solvent, solvent, solute, solvent. If the solution gets extremely hot, what about it? Okay? That's the only step. The solute solvent is the only step that's exothermic, right? So it must be extremely exothermic. It's much more exothermic than the first two steps are endothermic. That's that energy of hydration. That's the water molecules attaching and pulling the H's off of this sulfuric acid. It's the water attaching to the H plus releases a tremendous amount of energy. So all acids tend to get hot when you dissolve them in water because the water attaching to the H plus is extremely exothermic. Okay? So that's just the process. So I understand now what you're saying is because now we have 300 milliliters of an acid solution, but it's already been diluted, the heat's been dissipated, so adding more water isn't going to cause more of the reaction. This water pulled all the hydrogens off and did all the reacting that it's going to do. Then the rest of the water just dilutes it. Okay? So you get as much water. So what you don't want to do is put like 100 milliliters in here and then add the acid to it. You want to have as much as you can. See, there's 83. I don't trust the markings completely, so I want to have a little margin for error. So I put 300 to 350, pour the 83, then add just a little bit extra water to get to the 500. Okay? So if we look at a problem that is on concentration problems. If your Chromebook, you can go to page 160. If we look on page 160, number 77, it says pure acetic acid, known as glacial acetic acid, is a liquid with a density of 1.049 grams per milliliters. Calculate the molarity of the solution made by dissolving 20 milliliters. We're just going to say, what is glacial acetic? I'm just going to make a problem up instead of this one. Never mind. I don't like that problem. There is a problem in there. I just didn't write it down. Ladies, killing me. 50 milliliters, start copying this down. 2.5 molar solution is diluted to okay. So how do we do this one? Let's go ahead and start working on this one. It's very simple. It should take you about 30 seconds at the most. Anthony, focus. There it is. All right, you should be done by now. We plug into the formula. What's the molarity of the concentrated? Molarity of the concentrated. Okay, refocus now. 2.5 is the molarity of the concentrated. What's the volume of the concentrated? 50. Okay? And we know it's equal to the molarity of the dilute times the volume of the dilute. Which one are we looking for? Molarity of the dilute. So we're just going to bring the volume of the dilute over here. And so it's going to be 300 milliliters is equal to the molarity of the dilute. So it's going to be 5,300 as concentrated as it once was. It's always just a ratio. These problems are very similar. Whenever you're doing a dilution, it's always just going to be, and when we get into, equilibrium and even into acids and bases and looking as we're mixing things together, we're going to have to look at what's the diluted concentration once we mix the acid and the base together. Well, it's always just going to be this ratio of what did you start with to what did you end with. It's just that ratio. So what does this come out to? 0.41, and we have 3 sig figs, so it should be 410? 418 molar. Okay? So that's just, if you have a dilution problem, if it's a question that asks, what's the new concentration or how much water you have to add to make the concentration change, you're staying in the same solution. Notice there's no chemical reaction mentioned. It's all just adding water to the same solution. All right, 2 quick factors and thing now I want to talk about, and then I'm done. Sure. All right. How do we make put your phone away. That's a calculator? It looks like you're sliding.
I'm trying to figure out how to change the fraction to this.
Okay. All right. How do we make sugar dissolve? Y'all, you're just driving me crazy here. Okay? You have to realize that your talking distracts everybody else. And so even though you may not want to listen, the other people want to. Okay? And everybody wants to do well. And you're oblivious to the world. Now, how do you make sugar dissolve in tea faster?
Heat it up.
Okay? Heat it up. And what does that do? Why does that make it? Molecules are moving faster. Again, in order for a solute to dissolve, there has to be that solute and solvent have to touch, so the attraction, so the solvent can attack the solute and pull it into solution. So they have to touch. So if you heat them up, you speed them up. So by speeding molecules up, they're going to have more collisions, and therefore you'll touch more, and then they're going to dissolve faster. Okay? How else do we make them touch more? Stir it. Stir or shake. Okay? Again, that's just going to make them touch more. And thirdly, if you got that piece that just won't dissolve, what do? Crush it, because what does that do? Increase surface area. Okay? Crush it to increase surface area. Now, what does that mean, surface area? Why is that, again, in terms of solute, solvent?
More atoms or molecules of the solute are touching.
There's more solute edges exposed. When you have more surface area, there's more edges or more solute molecules that are actually going to be exposed, where the solvent can come and touch and cause it to dissolve. So again, everything about dissolving is about that solute to solvent attraction. Like dissolves like, polar dissolves polar, nonpolar dissolves nonpolar, is all about that solute to solvent attraction. In nonpolar molecules, they only have weak London forces. Water has London forces, dipole-dipole, and hydrogen bonds. Water's attractive forces for itself are way stronger than its attractions for the nonpolar solute, so they don't dissolve. On the other hand, water is very polar, so it's very strongly attracted to the ions and ionic compounds, so the positive end of the water, the hydrogens attract to the negative ions, the negative end, the oxygen attracts to the positive ions, strong solute to solvent, large energy of hydration, and so it pulls it into solution. Okay, so it's all about solute-solvent. Okay? Now, so that's just three easy things that are common sense. Now, there are two factors that affect how much dissolves. Two factors that affect the amount of solute that dissolves. Okay, and we talk about that as being the solubility. Talk about the solubility of something. We always talk about the maximum amount that can dissolve. So what do you think one factor is that affects how much something's going to dissolve? Temperature. For most solids and liquids, an increase in temperature does what to solubility? Increases solubility. Okay? Now, in terms of energy, for most solids and liquids, this is actually going to be an endothermic reaction. So in other words, you heat the sugar up, you're going to get more sugar dissolved in hot water than you are in cold water. So we got a flashback again. I know with Graeber you guys barely touched on this, but Le Chatelier's principle. Le Chatelier. Okay, Le Chatelier's principle. Does anybody remember what it is? L-E-C-H-A-T-E-L-I-E-R-S. Actually, apostrophe S. Le Chatelier's principle. Anybody? Nobody?
Or the equilibrium law can be used to predict the effect of a change in conditions on a chemical equilibrium.
All right.
All right. The back and forth.
It's a back and forth thing. When it's a system, when a stress is applied to a system at equilibrium. So here's our system at equilibrium. We got sugar sitting at the bottom of a glass of iced tea. You stirred it, you've shaken it, you've done everything, you've got the maximum amount of sugar dissolved. And then we apply a stress such as heat. The equilibrium is going to shift in such a way as to relieve the stress. Okay? So by adding heat, we're going to say this equilibrium is saying, ooh, it's getting hot in here. We need to use up that heat. So it's going to shift away from whatever's being added. So it's going to shift to the right to make more of the solute and the solvent come together and make more solution. More sugar is going to dissolve. In any endothermic reaction, adding heat makes it go left to right. Alex, why do we keep turning around? Stay focused. Anytime you have an endothermic reaction, adding heat makes it go left to right. So most solids and liquids are a positive heat of solution, meaning that it's endothermic, so heat's over here on the left. So you increase the temperature, you increase the solubility. Now, heat has varying effects, and so if you look in your book, is that? I think it's chapter 13, actually. Turn in your books or your Chromebooks to page 543. Okay, so this is on page 543 in your book. Okay, it's in every single chemistry book ever written. Okay, but it shows the difference in solubility, the maximum amount that can dissolve as a function of temperature. So as you increase the temperature from 0 to 100, how does the solubility change? Notice for most solids and liquids, the solubility increases. Now, it increases by different amounts. Okay? Notice salt has a very almost horizontal line. Salt's heat of solution is very near 0. It's barely endothermic at all. So that means that delta H1 plus delta H2 is just about equal to delta H3. The endothermic steps just about equal the exothermic steps. So when you add them together, it comes out nearly 0. Just barely slightly positive. So temperature has a very little effect. The ones like potassium nitrate, they have a very positive heat of solution. Temperature has a big effect on them. But you look over here at cerium sulfate, that solubility actually decreases. So what's the sign going to be for this heat of solution? Negative. Negative. So if we go through then and put that here, okay, if it's exothermic, we're going to say solute plus solvent goes to solution plus heat over here, because heat's being released to the surroundings in an exothermic reaction. So if I add heat, which way Le Chatelier's principle says it's going to go which way? Right to left. So that means that solute and solvent are going to separate from one another. It's going to precipitate out when you heat it up. And that's very rare. You only saw one thing, cerium sulfate, which we've never ever heard of. Okay? So this is rare for solids and liquids. Most solids and liquids are exothermic. Endothermic. Increasing temperature increases solubility. Okay? But all gases, okay? All gases, as temperature increases, solubility decreases. So what does that make them? Positive or negative heat of solution? This is going to be a negative delta H of solution. So if we come back to this graph, blank. If we come back to this graph and look on the other side, here's your gases. Notice that all gases, the solubility decreases. This is why the amount of oxygen in the summertime, the amount of oxygen in lakes and rivers and streams is actually less. You're much more likely to have a fish kill where they die due to lack of oxygen in the pond in the summertime than you do in the winter. Because at the higher temperatures, you have lower oxygen solubilities. Okay? So temperature always decreases the solubility. CO2, the fizz and pop, is going to go flatter much faster if you leave it out in the sun than if you have it in the refrigerator. because the extra heat drives that out. If you try to open up a hot 2-liter bottle, it's going to want to really fizz and come out because the solubility of the CO2 is way less at the higher temperature than like if you left it in the trunk of your car in the summertime and then you took it out and you tried to open it. It's probably really going to fizz versus if you took it out of the fridge. It's not going to fizz over hardly at all. Okay? So all gases are exothermic. They have a negative heat of solution. Solubility decreases with temperature, whereas most solids and liquids increase in solubility with temperature, but there are a few that actually decrease. Okay? So that's the first factor. What do you think the second factor is? What's the second factor that affects solubility? How much dissolves? No, that's what solubility is. It's the measure of what's the maximum amount that will dissolve. No, because it's always going to be a ratio. The solubility, it's always going to be, and that's a good question. If you look at those graphs, it's always grams of solute per 100 grams of solvent or per 250 grams of solvent. It's always per a set amount of solvent. Okay? The second one is pressure. Did somebody say it? I didn't hear it. Pressure. Pressure has no effect on solids and liquids. So adding pressure doesn't do anything to make more sugar dissolve, make more salt dissolve, nothing. Pressure only affects gases. Okay? For gases, an increase in pressure increases solubility. More pressure, more soluble. This is why they call pop pop. Because when you open the pop top, it makes a sound. Okay? They call it, the pop top that you open it up, you're releasing the pressure. What's the first thing you immediately see in a 2-liter bottle as when you open it up and release the pressure? It fizzes, it bubbles. You see the gas beginning to come out of solution immediately. Okay? Because you've gone from 5 atmospheres of pressure down to 1 atmosphere of pressure. By decreasing the pressure, you've decreased the solubility. It follows what's Henry's law. It's a direct proportion. And you don't have to know Henry's law, but it's simply increase pressure, you double the pressure, you double the solubility. You triple the pressure, you triple the solubility. That's Henry's law. Now, this is the big deal if you ever go scuba diving.
So when you pour soda in the glass and it's fizzy and then it goes down, is that when the CO2 is going?
Yeah, the CO2 is coming out of the solution. That's why it gets fizzy. That's why I don't like to pour it over ice. I like to drink it straight out of the can because then I don't lose all that fizz when you pour it over the ice. Okay. Now I have a really good friend. He doesn't like the fizz, so he tries to get as much out. And he pours it over the ice and lets it sit. And I don't know why anybody would like a flat Coke, but I know it's just nasty. He's just stupid. And so I tell him that all the time. You're missing out on the best part. Feel the burn, baby. That's the best part. So if you go scuba diving, and you go down 30 feet, every 33 feet is 1 atmosphere of pressure. So that doubles the pressure on your body. That doubles the amount of gases that can dissolve in your blood. So you're down at 30 feet, 50 feet, 75 feet. You're down there for 30 minutes. Now all of a sudden your blood is just concentrated, not only with oxygen, but with nitrogen, the other part of the air. So you have that compressed air, you're breathing it in. And then all of a sudden you see the great white shark, Jaws 10 comes into your mind. You're the new, shark bait. And so you get freaked out and you go flying to the top. What happens? You get the bends. Okay? You're basically a soda can under pressure at the 100 feet, 75 feet. You're under pressure now. You have all that gas in your blood. and then you race to the top, it's like opening up the pop top. It's like shaking up a 2-liter bottle and opening it up. All of a sudden now all that extra gas wants to come out of a solution immediately. So your blood actually starts to fizz. And the gas, all that dissolved nitrogen begins bubbling out and it collects in your joints and it's extremely painful. And it's called the bends, and it's painful enough to where it can kill you. So the way that they treat you is that they put you into a barometric pressure chamber, repressurize you, and then to hopefully get that to redissolve and then let it come up, let it just come out slowly. The oxygen isn't as much of a problem because you're breathing that, you're using that because you're scared, you see the shark, you're breathing fast, your body's needing all that oxygen, and so the oxygen doesn't build up, but the nitrogen is just there. It doesn't do anything, so it just builds up. You can't get rid of it fast enough. Now, I was actually watching a show about, it was like over in the Philippines or some Pacific island, and they just dived down for oysters. And, I mean, these guys are just breathing through like a little tube. It's not like a scuba tank or anything. They just have a hose connected to them, and they're breathing out of it. But they're down there for, 30 minutes to an hour, down scoping the bottom, scraping up, trying to get the oysters, just to make a living. And then they come up. Sometimes they come up too fast, and they get the bends. They just send them back down to the bottom and tell them to come up slow. I mean, but it's a very dangerous occupation for me. It was just talking about how so many of them have, die, and there's the dangers, and the hoses get tangled, so they don't have any oxygen, and it's just really bad. But I mean, they just simply go back down to the bottom. It's over in the Philippines somewhere where they're trying to harvest oysters, and so they have these. It's just a very primitive system that they use. Anyway, so pressure has no effect on solids and liquids, but gases is directly proportional. Double the pressure, double the concentration. Okay? So, for the rest of the period now, I want you to kind of practice doing these. Okay, so we already have these, and hopefully you're pretty close to being done there. And now we're going to add to that. Where's my list? Here. Oh, it's in this book. What say do you want?
If we didn't finish,
Yeah, just you got to start there. Start wherever you finished yesterday. Okay? So, we're going to go through, we're going to use today. Now, we need to work diligently. We're going to work hard in class so we don't have to work hard out of class. If you guys are screwing around, that's what I'm saying, is if you work hard, if I feel like you're actually using your time wisely, we'll just figure out where everybody is. But if you're just kind of socializing the whole time, then it's going to end up being homework. Okay? So do the best you can. We work hard in class so we don't have to work hard out of class. Okay? So try to get these done. Once we get to the end here, I want to do a couple together to kind of get you an idea.